if you can see this board or not. Okay, are you ready? So now what we're doing is you're going to your notes that you took for 3.1. The first thing you want to look at, did you add it on to your table of contents yesterday? If you didn't, you have to add it today, right? Today's the 22nd, right? 9/22. Reading. What section is this? Is 3.2 or 3.1?
3.1.
1 was yesterday, but today we have to have 3.2. You understand what I'm saying? What pages is that? 68 to 74. 68 to 74 and 9/22. Practice problems. So that's after the lecture today. That's where you should be after, okay? So let's talk about this. The definition is what I wrote in my book of non-uniform motion diagram. In your notes, do you have velocity is changing? In your notes. Okay? Non-uniform motion diagram is velocity is changing. Do you have that in your notes? If not, add it to your notes. Okay? Next thing, in your notes for yesterday, which was 3.1, what you were working on at the very beginning. In the question today, I asked you what the difference between motion diagram and particle diagram is. What is the difference? What is the difference?
Particle diagram will have the dots on it, and the motion diagram has the picture.
Yes. So motion diagram, here we have a person at rest. This person is moving at equal space over a constant speed, right? This one, the person is moving faster, and this one is slowing down. These are motion graphs. But if I ask you to use the particle model, what would the person motionless look like?
2 dots close together, and then just slowly get spread more out.
Just one dot. He's not going anywhere, is he? Okay. How about somebody at a constant speed? What does that look like?
Equal.
So you have dot, 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 and they're equal. Right so far? Okay. We can actually put vectors in here too, can't we? They have to be the same though. How about this one with something speeding up?
You're going to start them out close and then slowly start spacing them apart depending on how fast they go.
Okay. I put them where my people are. What's going on with my vector lines? They should be further apart and they should be longer. Got it?
Mm-hmm.
So that's that one. How about something slowing down?
You'll start long, you know, short.
I'm just doing my dots where my people are. Does that make sense? So if I ask you to draw me these two diagrams and call them by name, motion diagram and particle model, would you know the difference? Okay.
Yes, ma'am.
So what I'm going to do is I'm going to erase this. And what I'm doing is I'm just going over the things I thought was important. There's a formula that you need to have in your notes. Now, I personally wrote it. And what I'm going to do is I'm going to take my highlighter and I'm going to highlight it. What do you think I'm highlighting it for?
It's important.
When I have a test, I want to find it. Okay? What is the formula for displacement acceleration? I'll put it over here. So turn it. I think I'll go over some more. Perfect. Okay. It is this one. Do you have that one in your notes?
Yeah.
If you do, highlight it.
What's the name of the?
This is the change in velocity equals velocity final minus velocity initial equals to velocity final plus a negative velocity initial. Now, why do I have that set up that way?
Is it kind of to check your answer, make sure it's right?
If it is a negative velocity, so in other words, what I'm talking about, say you're going this direction, and then you're going in that direction, right, sir? You changed your velocity, didn't you?
Mm-hmm.
So why would we add a negative V1?
Because you're going backwards.
Because I'm going backwards, and you cannot subtract a negative, can you?
Mm-hmm.
So that's why you're adding a negative. Everybody good so far?
Mm-hmm.
Do you have it in your notes, and did you highlight it? Now, take out your board. Open your textbook. To page 70. And draw that graph. And the graph that I'm asking you to draw is I'm asking you to draw figure 13, please. Figure 13. On page 70. Oh, wrong page, wrong figure. God bless me. I'm sorry, on page 63. My fault, I'm getting ahead of myself. Page 63. And it's figure 5. You have it drawn. Now, I'm making you do those here today on the boards, but when you're at home, I'm gonna give you this graph paper, and you'll have to do them on there and have them to prove that you did it. I personally can look at yours to make sure yours is done, but at home I cannot. And this would be part of your picture for Wednesday and Thursday. Okay? So here, we're trying to find slope. Now, let's do this really quick. Dries over here, mixes over here. Okay? We have our time down here, and we have our velocity in meters per second here, right? So to be able to find our slope, and our slope is represented by this M, you're going to do rise over run. Now, how do we do that? How do we get 10 meters per second and then 2.0 seconds? How do we get that? Yeah, we look and see where it's at, right? And we just do that. So the answer to this question would be what with your calculator? Yeah, 5. 5 what? Well, squared. So if you're asking for a slope, to be able to do that, you have to do your rise over your run. Rise goes up, run goes across. Do you understand how to do that? So if you draw one and you have a question on the test, you should have your graph paper, you should draw it, show me your math, and do me a favor, square it to show me. And when I mean square it, that means put a box around it to say, this is my answer. Is everybody good? Okay, erase your board. And just set it aside. There was another thing in the reading assignment where it showed something, and it's on the bottom of that page there. What is this? So we have an A here, right? We've got a B, that's here. We got a C, that's here. And we have a D that goes up. And then we also have an E that goes straight across. What is that? What type of graph is that? And I'm on page 63 of your textbook.
Acceleration graph?
Velocity versus time, which would be acceleration, correct. So, what's going on with these runners?
They're accelerating and stuff at different speeds.
Nah, they going at this. Well, 2 of them are going at the same speed. Well, they're going at the same speed, just starting at different places.
That's velocity versus time. This has nothing to do with displacement, does it? Has nothing to do with what we did yesterday, where we talked about the starting line and somebody was in front of the starting line, somebody was behind the starting line. This has to do with velocity versus time. This person here has the constant velocity, right? This one here, what do they have? A constant velocity. What's going up here? They're accelerating. What's C doing? Deaccelerating. What's D doing? Accelerating. So write yourself a note. When you look at velocity versus time, you're looking at, is the line going up? Is it going straight across? Or if it's going down? If the line is going like that, that means they're increasing. If your line is going this direction, that means they're decreasing. And if it goes straight across, what does that mean? Constant acceleration. That means they didn't go faster or slower. They're at the same rate as they go through. Does everybody understand that? Everybody good? Okay. Now what we want to do is now we want to talk about, we want to go to the next page, which has a sample problem on it. So let's look at it. 65. It says example problem number 1, velocity and acceleration. How would you describe the sprinter's velocity and acceleration shown on the graph? So what is going on with the sprinter here? We got several different things, don't we? How many sprinters do we have?
3.
I see 2.
There's 2 red lines and there's a blue line.
Yes, there is. So why are they, so they're doing just the math for 2 of them. One of them is going to be at time 1.0 seconds and at time at 5.0 seconds. So there's 3 runners, but they're only asking a question about 2 of them, correct? So the first one is they're doing the one that is the 1.0 seconds. So if we're looking at that, they're doing 10 minus 6. Where are they getting that from?
That's the amount of time where.
Ain't that where the line?
Where are they getting these numbers from? Because that was, to me, when I looked at it, it was very confusing. This one? Mm-hmm. What are they doing here? Where are they getting this numbers from? I don't see it. Do you see it?
It's 6 where the 2 runners meet.
Mm-hmm. Where they meet. Perfect. Can we go on to the problems instead? Because I thought this example problem was just crazy. I didn't understand what they were doing. We do need to add one more formula, don't we? Over here? What is the other one we need to add to this?
Average acceleration?
Yes. Okay? Average acceleration, which is the line above the A, equals change in velocity over change in time. Change in velocity is what? What is my equation for change in velocity? Well, Miss Sloan, is velocity final minus velocity initial. What is the change in time? Time final, correct? Minus time initial. Okay? Let's go to question number 1. God bless us. On page number 66. So it says the velocity time graph in figure 8 describes Steve's motion as he walked along the midway of the state fair. Sketch the corresponding motion diagram, including the velocity vectors in this diagram. So what does your diagram look like? On your board, show me what you got.
You on page 66?
I am on page 66, sir. And I am doing practice problem number 1 at the very top. The only thing I'm asking you for is to take this velocity time graph and give me a motion graph, please. Or a motion diagram. And you're using that graph right there, baby. All right, you have your board in front of you. Look and see if yours looks like mine. Did you, on 6 and 7, did you put a dot on the top and a dot on the bottom with a vector? Because he stopped there for a little bit, didn't he?
Yeah.
6 to 7? If yours is not correct, change it on your paper for the answer to question number 1. Just roll what I've got on the paper. That's great. Looks good. Very good. So that's the answer to question number 1. Question number 2 says, using a velocity time graph of a toy train in figure 9, answer these questions. A, what is the train's speed constant? B, during which time interval is the train's accelerated positive? And C, when is the train's acceleration most negative? So for A, the train speed was from 5.0 to 15.0 seconds. Is that the answer that you had on your paper? Just not fix it. On your paper ISM book. B, time interval was from 0.0 to 5.0 seconds. And C, acceleration was from 15.0 to 20.0 seconds. Is that the answer that you had for 2A, B, and C in your ISM book? Give y'all a few minutes. Now we're going to go to question number 3. Question number 3 is we're using a figure. It is asking us to find average velocity of that graph, right? So for number 3, refer to figure 9 and find the average acceleration of the train during the following intervals. From 0 to 5.0 seconds. So, average velocity equals velocity final minus velocity initial over time final minus time initial. What is my velocity final from that time? 0 to 10, right? So it would be 10 seconds minus 0 minutes per second, right? That's my velocity final and my velocity initial, isn't it? What is my time? 5.0 seconds, subtract 0.0 seconds. Get your calculators out and do the math, please. Remember, you're going to use the AB function. Go ahead. What did you get? 2. Correct. 2.0 meters per second. What's my answer in? Squared. Thank you, sir. That is 3. Question number A. B. Are you ready? So we are going from 15 seconds to 20 seconds now. All right. What is my velocity final for that time? For 20 seconds, what's it equal to? How many meters per second?
4.
4, right? 4.0 meters per second. And we're going to subtract that from our 20. And what is that?
16. Oh, no.
20 seconds. How much is that?
17.
20 seconds.
Where's that? That's wrong.
20? Wait. You said 20 seconds?
Yep, 20 seconds. We're doing 15 to 20 seconds. I have 10.
That's what I didn't know if it dropped.
10.0 meters per second. And we're going to divide that by our 20 seconds, subtract our 15 seconds. Go ahead and do your math on that. What did you get the answer for that one?
-1.
Negative 1 point, and I rounded mine to 2 meters per second. Very good. Okay, are you ready to go to C3 now? Ready to go to C? Now C says that we're doing it from 0 seconds to 40 seconds. What is my numbers here? What did you do? What did you get on yours? I'm on 3C. Okay, what'd you get? 3C.
3 meters per second.
What numbers did you use?
I just guessed 3 also.
Fantastic. So what is my velocity final here, sir?
Velocity final.
Yes, sir, for this question. It is from 0 to 40 seconds.
40 seconds. The final velocity is 0.
Final velocity is 0. What's my initial velocity?
0.
0. Okay. And we're going to divide that by our seconds. What is our seconds again? It told us
40.
40 minus 0, right?
It's going to be 0.
And my answer is 0.0 meters per second squared. Perfect. Thank you, sir. I'm going to do 2 more. 6, 7, 8, or 9. Which ones would you like to see?
6.
6? All right. Question number 6 says, the race car in the previous problem showed slows from 36 meters per second to 15 meters per second over 3.0 seconds. What is the average acceleration? Well, what formula are we going to use? Can we go to 5 first? Because you have to have that, don't you? What did you find for your average acceleration for number 5? Let's start with velocity final minus velocity initial. What is my final velocity for number 5?
Final velocity.
So it says a race car forward velocity increased from 4.0 meters per second to 36 meters per second. My velocity final is 36 meters per second, correct? What's my initial?
Your initial is going to be increases from 4.
So that would be my initial, which would be 4 meters per second. Okay? So I'm going to say 36 meters per second. Subtract 4 meters per second. What is my time? How long did we do it for?
Get it in 4 seconds.
4 seconds. We don't have to do a velocity initial or final, do we? I mean, time initial or time final. We just got to do average time, which is what?
4 seconds.
4 seconds. What's my answer? Put it in your calculator. 8 for 80 cents. 8.0 meters per second squared. Okay, let's do number 6 now because we had to have that. Okay, on number 6, it says, the race car from the previous problem slows from 36 to 15. Okay, what is my final velocity?
15.
15 meters per second. What's my initial one?
36.
Started with 36. What is my change in time?
3 seconds.
So what's my answer?
Can you have a negative?
Good, yes. Because he deaccelerated, right?
Yes, ma'am.
What do you have?
-7.
Okay. So that's 7.0 meters per second squared. You can have a negative or a positive. Why are we not worried about the sign?
Because it's a change. It's not measuring what it changed by.
Perfect. You got it? Okay. So I did those 2, but I'll do one more. Which one would you like to do? They're all the same. 7, 8, or 9?
7.
7. Number 7 says, a bus is moving west at 25 meters per second when the driver steps on the brake and brings the bus to a stop in 3 seconds. What is the average acceleration of the bus while braking? So, we're trying to find A, right? Which is equal to the same thing as average velocity, right? Excuse me, average acceleration of change in velocity over change in time. Same formula. So what is my change in velocity for number 7? He comes to a stop, doesn't he?
Yeah.
And so my final velocity is 0 because he came to a stop. And I'm going to subtract that by my initial. How fast was he going?
25.
Right? Okay. Now, what was my time?
3 seconds.
Average was 3 seconds. If I do my math, what do I get?
-8.
Yep, negative 8.3 meters per second squared. But now it's asking me for direction. What direction is he going?
He's going.
He's going in, if he's
going
going,
west.
if he was going west, what's the opposite of west?
East.
East. So it's 8.3 meters per second east. Because you said, doesn't matter about the negative part, but depending on which direction he is going, it's going to change this. Because if I kept it a negative, it would not be east, it would be what? West.
So does that mean he started going in reverse?
Yes.
Okay.
Good job. Okay, and number B, ask me, if the bus took twice as long to stop, how would the acceleration compare to what you found in part A?
It'd be half of that.
Half. So half of that is what?
It'd be 4.15 and one something.
That's close enough. And there's your answer. Everybody good?
Mm.
So for the ones I didn't do, for number 8, I got 3.0 meters per second squared. And for number 9, I got 0.28 meters per second west. Do I need to repeat that so you can check your answers? Freddie, you need me to repeat it.
You said, I got 8.
8 is 3.0 meters per second squared. And number 9 is 0.28 meters per second west. So I'm going to stop the recording.